K-Tutorial number 1, Defining Lambda, Lesson 1. Here we define our first K module, which contains the initial syntax of Lambda, and learn how to use the basic K commands. I have just created an empty working folder and opened the terminal window to the left and an editor window to the right. We will edit our K definition in the right window in a file called lambda.k, and we'll call the K-tool commands in the left window. Let us start by defining a K module containing the syntax of Lambda. K modules are introduced with the keywords module and module. The keyword syntax adds new productions to the syntax grammar using a BNF-like notation. Terminals are enclosed in double quotes like strings. You can define multiple productions for the same non-terminal in the same syntax declaration using the vertical bar separator. Productions can have attributes which are enclosed in square brackets. The attribute left tells the parser that we want the Lambda application to be left associative. The attribute bracket tells the parser to not generate a node for the parenthesis production in the abstract syntax trees associated to programs. In other words, we want to allow parentheses to be used for grouping, but we do not want to bother to give them their obvious ignore semantics. In our variant of Lambda calculus defined here, identifiers and Lambda abstractions are meant to be irreducible, that is, are meant to be values. However, so far, val is just another node terminal, just like exp, without any semantic meaning. It will get a semantic meaning later. After we are done typing our definition in the file lambda.k, we can compile it with the command compile lambda.k. If we get no errors, then a parser has been generated. This parser will be called from now on by default by the krun tool. To see whether and how the parser works, we are going to write some Lambda programs and store them in files with the extension .lambda. Let us create a file identity.lambda which contains the identity lambda abstraction lambda_x. Now let us call krun on identity.lambda. Make sure you call the krun command from the folder containing your language definition. Otherwise, type krun --help to learn how to pass a language definition as a parameter to krun. The krun command produces the output shown in the command window. If you see such an output, it means that your program has been parsed and then interpreted correctly. If you want to see the internal abstract syntax tree, or AST, representation of the parsed program, which we call the KAST, then type cast in the command line instead of krun. You should normally never need to see this internal representation in your K definitions, so do not get scared. Yes, it is ugly for humans, but it is very convenient for tools. Note the krun places the program in a K cell. In K, computations happen only in cells. If you do not define a configuration in your definition, like we did here, then a configuration will be created automatically for you which contains only one cell, the default K cell, which holds the program. Next, let us create a file freeVariableCapture.lambda which contains an expression which, in order to execute correctly in a substitution-based semantics of Lambda, the substitution operation needs to avoid variable capture. Next, file closedVariableCapture.lambda shows an expression which also requires a capture-free substitution, but this expression is closed. That is, it has no free variables, and all its bound variables are distinct. I believe this is actually the smallest such expression. Finally, the file omega.lambda contains the classic omega combinator, or closed expression, which is the smallest expression which loops forever. Not now, but after we define the semantics of Lambda. Feel free to define and parse several other Lambda programs to get a feel for how the parser works. Parse also some incorrect programs to see how the parser generates error messages. In the next lesson, we will see how to define semantic rules that iteratively rewrite expressions over the defined syntax until they evaluate to a result. This way, we obtain our first programming language defined in K.